you go to PubMed and you look at the neuroscientific literature and you look at keywords such as graph and brain, you find that there's thousands, in fact, 7,500 roughly results that have been produced. And that's because graph theory has been really successful in neuroscience. So this right here is a figure from a recent paper that I took that shows the overall approach. And the idea, quite simply, is that we can take different kinds of brain data. So on the left-hand side, anatomical data, on the right-hand side, functional data, and we can express these data in terms of graphs. And if you just visually look at these graphs, it kind of looks like a brain, or what our understanding is of a brain, and that we think of the brain as a network, as nodes, if you will, or vertices that are connected and interact. And so that would be the edges of a graph. Well, my point that I want to make today is that that is actually not what the brain does. So a graph, by definition, is binary, expresses binary relations, which is that there's only one line between 2 points. So in other words, there's one edge between 2 nodes or 2 vertices. But in neuroscience, we actually deal with something that's more complex. And I tried to show this here symbolically with this diagram, where they're showing the idea of a Hebbian synapse. What I'm showing here is the inputs x1, x2 to xn. So these might be all different neurons onto another neuron. That's the circle in the middle. And that circle produces an output, y. So typically the way that we think about it is that what neurons do is that they get a variety of inputs, in this case, x1, x2 until xn, and they sum these inputs up, and if they cross a certain threshold, then they provide an active output. So that's the idea of an integrate and fire neuron. The other thing that's shown right here is these W's, W1, W2, and so on. Those would be the synaptic strengths, if you will, or how much the inputs are weighed for all of these different neurons that are providing input to that one neuron. Well, what you can see here already is that instead of just having a one-to-one relationship with a node, we're dealing here with many different edges. There's more than one edge. There's many nodes, and they all come together. The thing that concerns me, though, is that each of these arrows right here is still just a binary relationship. It only symbolizes the impact of a single neuron in isolation. But when it comes to neuroscience, we know that there's more going on. So I'm showing right here a simplified version of this graph to make it a little bit more simple. I cleaned it up. So we only have x1 and let's say x2 as another input neuron, and they both converge. They both provide inputs to the neuron that we're interested in that produces the output y. And I'm showing right here data from a Nature paper that was published by Clay Reed's lab with Marty Asri and Jose Manuel Alonso, where they ran across a very rare instance where they got lucky enough to record 3 neurons at the same time in the brain of an animal that were all connected. So what I'm showing right here at the top, A and B are receptor fields of 2 neurons that are in the thalamus of an animal, and then neuron C is in the visual cortex. And what we know about the anatomy of the brain is that neurons A and B, when they're connected to neuron C, they must converge. It's pretty much the same situation that I'm showing on the left-hand side. So you can think of X1 as A and X2 as B, and these neurons are firing. And when they fire, they provide inputs onto neuron C. So what I'm showing below these blue dots, which show the receptor fields, are cross correlations. And they indicate that when each of these neurons is active, with a little bit of a delay, which we expect because there is a synapse in between, neuron C gets active. So that is a pretty strong evidence that these neurons have a causal impact onto neuron C. Well, the interesting thing is that if we look at the pairwise relationship, so we look at the isolated input or the effect that A has on C and that B has on C, we can also ask, well, what happens if both fire at the same time? And so that's showing right here in the middle. So when A and B are active at the same time, it turns out that neuron C also gets active, but we cannot predict how. Isolated activity of neuron A and of neuron B, if we know the causal impact of each, does not allow us to predict or find out quantitatively what the combined activity of both of them is. So when both neurons are active, A and B, something happens that is close to emergent. Something new happens, something that cannot be described just by studying the pairwise relations. There's a tertiary relationship between these neurons. And that is exactly what hypergraphs are all about. So what I'm showing right here, again, are 3 nodes, N, N, and N. And the traditional way of thinking about a graph would be shown in blue, where we can connect a line or an edge between individual nodes. But what I just showed you is that what happens in the brain is that when 2 neurons are active at the same time, they combine their effect. And that would be shown right here with the black lines, where the 2 edges, if you will, from the nodes combine and provide a new combined input onto the 3rd node. And that is what we call a hyperedge. And whenever we're dealing with hyperedges, we're dealing with hypergraphs. So if we take this example from before, the edge would be that we're studying each of the causal effects of these neurons onto the cortical neuron in isolation. But what the Nature paper showed is there's a combined effect that we have to investigate as a hyperedge. Now, hyperedges can also be thought of or shown and graphed in different ways. So this is a different way to think of a hypergraph, where each of the letters here, the circles A, B, and so on, those are different nodes. And then what you see in colors, what kind of looks like rubber bands that stretch between them, are hyperedges. Each time that you see here a hyperedge that spans more than 2 nodes, so the green would be a regular edge in a graph, but then the blue and the orange rubber bands, they show you that there is a non-pairwise relationship. It's a hyperedge. But if you look into PubMed and you type in hypergraph and neurons, you only get 8 results. Hypergraph and brains, only 48 results. So what I'm telling you is that even though we've studied the brain a lot and we've been using graph theory, when it comes to what might be the most fitting type of graph theory, namely to generalize the hypergraphs, there's almost nothing done yet. And hypergraphs are also interesting for when this idea of looking at brain activity that might give rise to qualia structure, in particular, integrated information theory. So this is just a summary of integrated information theory that many of you might be familiar with. And it basically shows a hypergraph, which is that when we're talking about the cause-effect structure, or the CES, that neurons are creating that ultimately provide a structure, a mathematical structure that is isomorphic to the qualia structure, well, that structure is a hypergraph. In the language of IIT, it is described as a simplicial complex, and I'm showing this at the bottom. For those of you that are not familiar with that, a simplicial complex in a way is a special kind of hypergraph, where you start by having 0 simplexes, so those were the individual nodes. You can have a 1 simplex, which would be the edge in a regular graph between them. And the 2 simplex would be like a triangle shown right here. And that is basically identical to what I showed before, the hyperedge in a hypergraph, where you have the combined influence add on one thing. The only difference here, it's not directed as I did before. It's an undirected graph. And simplicial complexes are related to hypergraphs. There's ways to translate between them. They're not the same, though. I will probably come back to this topic later. There's